Welcome to the Interference Technology webinar, Cost-Effective EMC Design Working with the Laws of Physics. My name is Belinda Stachukevich, and I'm the editor of Interference Technology. Established in 1970, Interference Technology helps EMI and EMC engineers find solutions to their various testing, design, application, and regulatory issues by publishing articles, news, and other practical content. This webinar is presented by Keith Armstrong. Keith graduated with honors from Imperial College in London in 1972 with a Bachelor of Science in Electrical Engineering, specializing in analog circuit design and electromagnetic field theory. Between 1972 and 1990, Keith worked for a variety of electronics companies as electronic designer, then project manager and design manager. In 1990, he went independent with Cherry Clough Consultants Limited, providing design services to help achieve compliance with EMC and with safety, while at the same time helping to reduce time to market, design costs, unit manufacturing costs, and warranty costs. Now in 2012, Cherry Clough has had nearly 800 satisfied customers in almost all areas where electronics are used. This webinar will be interactive. You will be able to ask questions and answer polls, and we encourage you to participate. Take a look at your go-to navigation pane, the blue box on the right-hand corner of your screen. If at any time you have a question, we ask that you fill out the type box and hit send. To make the screen minimize and maximize, click the arrow buttons. To raise your hand to ask a question or report an issue, click the hand icon. And to maximize the screen, click the middle button. We will present the topic for 45 minutes, followed by a 15-minute question and answer session. Now Keith will begin the presentation.
Thank you, Belinda. Welcome, everybody. It's nice to be talking to you today. So, as Belinda said, the title is Cost-Effective EMC Design by Working with the Laws of Physics. So I hope you'll find this very useful. Now, like me, you may have been taught physics and or Maxwell's equations at university. But if you were, you'll remember it's never properly explained to us how this theory related to the business of circuit design, power supply decoupling, printed circuit board layout, shielding and filtering, and so on. It didn't tell us how to make the circuits function well or achieve EMC to improve our employees' financial performance, which of course is the reason we do it. So, because of that, many electronic designers use techniques that add delays, costs, and reduce profitability. They think they're doing the right thing, but they're not really. They'll often find they're requiring several design iterations to achieve the functional specifications, and then several more iterations to achieve the EMC test passes. And the result is lower profits and the higher levels of financial risk than you need to take. In fact, all electronics is about electromagnetic compatibility, which we call EMC. I call it either internal EMC or external EMC, and this should become clear in a second. EMC compliance, such as complying with the EMC directive, is only a subset of what I call the external EMC needed for customer satisfaction and low warranty costs. Physics and Maxwell's equations are used with some simplifications by electromagnetic field simulators, and they also lead to design principles that aren't difficult to understand and use. A good EMC design engineers usually learn to visualize the internal and external EMC, and maybe you will visualize them a bit better in a few minutes. This is what I call the entirety of Real EMC, and in there we have external EMC, which is like passing tests and actually working well in the real world, and internal EMC, which has a lot to do with functionality, terms we call like signal-to-noise ratio, overshoot, eye closure, power integrity, clock jitter, noise margin, ringing, signal integrity, crosstalk, and so on and so forth. All these terms are used to discuss problems or errors or difficulties with the signals, are really internal electromagnetic compatibility. Going back to the external world, You'll see I've got a little blob in there called EMC test laboratory measurements. It's meant to represent the amount of the real-world electromagnetic environment is covered by testing in laboratories. Actually, it's a lot smaller than that blob, but if I made it smaller, I wouldn't have been able to fit the words in. So let's derive some easy EMC design principles by summarizing the physics and the Maxwell's equations. But we're not going to use equations or difficult maths. This is the point where most academics jump in and start writing curves and divs and grads and all that sort of stuff. We don't need that. But we should get some design principles that are easy to visualize and easy to apply. Actually, these principles have been proven over 30 or more years to improve company financial performance in electronics. Then we're going to apply them to an example electronic product. First of all, AC and DC. These EMC principles I'm about to describe apply to all AC currents, whether they're associated with electrical power, DC, AC, radio frequency, femtowatts to terawatts, or electronic signals, analog, digital, switch mode, radio frequency, whatever, and all noise in any power supplies or signals, because they're currents too. When we learn circuit design, we're taught that DC currents flow downhill, if you like, from the positive rail to the 0 volts, or from uphill from the negative rail to the 0 volts. But AC, and that includes radio frequency currents, flow in any paths, regardless of the voltage potentials of the DC supply. They flow anywhere, in all directions, and they're controlled entirely by impedance.
Chief, I'd like to interrupt you for a minute to ask a poll question to our viewers.
Sure, yeah.
Attendees, please answer the following question. What paths do AC currents flow in? From the positive DC rail to ground, from anywhere to ground, or in the path with the lowest impedances? You have about 30 seconds to answer this poll. Answers are coming in. Thank you very much.
Okay, shall I carry on?
Sure.
Okay then, I'll carry on, shall I? To understand impedance, we need to understand, or at least know about, permeability, which we call mu, and permittivity, which we call epsilon, or E if you like. Now everything in the universe has permeability. And this is associated with inductive energy, which we draw as lines of magnetic energy. We use the symbol H for magnetic flux. And everything also has permittivity, epsilon, which is associated with capacitive energy, which we draw as lines of electric energy flow, or E, flux. And everything has resistivity, except for superconductors, of course, which have no resistance. Resistivity is associated with energy loss, the conversion of electromagnetic energy flow into heat. But it's permeability and permittivity which is going to be the most important to us. The routes taken by conductors and the permeability and permittivity of the medium, the air, the vacuum, whatever, cause inductance and capacitance to rise in those conductors. So we could be talking about wires, cables, printed circuit board traces, even bond wires on silicon chips. What this means is, whenever we have a fluctuating voltage, we always have a current associated with it. It's not possible to have a fluctuating voltage without a current. And it works the other way around too. If we have a fluctuating current, an AC current, there's always an AC voltage, a fluctuating voltage associated with it. It's not possible for us to have an AC voltage or an AC current on their own. Now, in insulators like PVC or air or fiberglass surrounded and printed circuit board, the permeability and permittivity cause effects which are similar to inductance and capacitance. What this means is whenever we have a fluctuating electric field, which we call E, there's always an associated magnetic field, and vice versa. Whenever there's a fluctuating magnetic field, there's always a fluctuating electric field associated with it. And everything that we think of as an AC voltage or current is really a propagating electromagnetic wave. It's electromagnetic energy, which we measure in watts. You've heard of watts, I'm sure, propagating as a wave in the medium, the air or the fiberglass or the PVC of the cable, with a velocity v, and you can see v is the reciprocal of the square root of the permeability times permittivity. You'll be familiar with E equals mc squared. The c squared is the speed of light squared, and that's nearly 300 million meters a second. And it's interesting to note that the speed of propagation of light, which is an electromagnetic phenomenon like electricity, is actually given by, it's actually created by the permeability and permittivity of everything that surrounds us. When you have other media that aren't air or vacuum, like they're plastic or fiberglass or wood or whatever, or water, then either the permeability or the permittivity is higher, and the result is a slower speed. And as this energy propagates as a wave, it creates electromagnetic fields. And this is true for every kind of electrical activity. Like I said before, it doesn't matter whether it means 60 hertz power for most of you, 50 hertz for me, analog signals or power digital signals, switch mode, pulse width modulation, radio frequency, microwaves, whatever. Every kind of electrical activity is a propagating electromagnetic wave, including all electrical and electronic noise. It's just a current like anything else.
Keith, I'd like to ask our attendees another question.
Sure.
What are signals, data, or power really? A, propagating electromagnetic waves. B, electrons flowing against conductors. Or C, voltages and currents. We'll give you a few seconds to answer this question. Thank you for answering this question.
Okay.
The majority of you have voted for A. And back to you, Keith.
Thank you, Belinda. So, in textbooks, you'll usually see this business of propagating electromagnetic waves drawn something like this. We have a magnetic field drawn perpendicular. That's the direction the field waves in, if you like. We have, and there it is waving, with a wavelength of lambda, the wavelength. And then we have an electric field drawn perpendicular to that, an electric field oscillating perpendicular to that, and the power is propagating along that black line there. That's the direction of propagation of the wave energy with the velocity v. This is a traditional way, as I said, of representing a line vector. Of course, the energy is usually propagating across some kind of volume or area in space. But if you could just see one line of it, it might look like that. Now, what I'm drawing here is send and return conductors in cross-section. The red one is the send one, the return one is the blue one. And if you look at the magnetic field lines, they're usually drawn like that. Now, the energy is propagating perpendicular to the screen along the wires. The electric field, sorry, the magnetic field wave. The magnetic field lines are usually drawn that way. Of course, they're not really lines. The best way to think of these is like contour lines on the map. So where they're crowded close together, you can tell that there's a high rate of change of magnetic potential, if you like, there's a lot of magnetic flux through there. Where they're far apart, there's very weak magnetic fields. And we can draw electric field lines like that. You notice the electric field lines always terminate on the conductors, where the magnetic field lines never do. Once again, where the electric field lines are close together, it tells you that there's a lot of electrical energy in that region of space between the wires. Of course, if I was to draw the PVC insulation around these wires, then it would modify these field patterns. Well, this would modify the electric field pattern because of its increased dielectric constant, its permittivity. Now, because of the principle of conservation of energy, there's always a return current into any circuit node. Say the collector of a transistor, or the drain of a transistor, that's emitting a current into a conductor, you know, a signal or something, there must always be a return current flowing into it. And it must be identical in every way to the send current out of that node. But of course it must be opposite in phase. This is how nature balances energy. If it wasn't for this, the drain of an FET could emit electrical energy, getting it from nowhere, getting it from the vacuum. You know, there always has to be a return current equal but opposite to the send current for every point along a conductor or in a transistor or anywhere. Now, the send and the return currents from a circuit node, in other words, a propagating electromagnetic wave, are emitted simultaneously and propagate through the impedances of the various media, air, conductors, and so on. Eventually, they meet up to create what we think of as the send and return current loop. Now, maybe like me, you grew up as a circuit designer and you're very familiar with current loops. You know, you send some current into something, it has to get back, so you have to provide conductors for it. But this is the, if you like, the electromagnetic engineer's view, is that the send and return current flow simultaneously. And this is to create a balance in the energy at every node along the loop. Where you've got where you've got multiple paths that a current could flow through. Now, this is very typical of a ground return, for instance, or a power supply connection, where there are many points that the current could flow through as it returns. The electromagnetic power flow, which you think of as a current, divides amongst all the alternative paths according to their loop impedance. So in the far field of electromagnetic source, and we don't have time to talk about near field and far field, but in the far field electromagnetic source, see, the electric and magnetic fields experience what's called the wave impedance, which is the square root of the permeability divided by the permittivity for the medium that they're flowing through, whether it's plastic or air or fiberglass or oil or whatever. In air or vacuum, this is approximately 120 pi ohms, which we engineers call 377 ohms. It's close enough. But in other media, it's always a lower impedance. In the near field of an electromagnetic source, the wave impedance isn't the root of the permeability divided by the permittivity. And it can be very much higher or lower than 377 ohms. Conductors, of course, have inductance, capacitance, resistance, so they too can have impedances which are higher or lower than 377 ohms. Remember, the electromagnetic power of the current divides amongst all the alternative paths according to their individual impedances. So it's a bit like say you've got a voltage, say 1 volt, and you apply it to a couple of resistors in parallel, and you've got a 10 ohm resistor and a 100 ohm resistor in parallel. Well, you get 9/10 flowing down the 10 ohm resistor and 1/10, sorry, I think it's 10/11 flowing down the 10 ohm resistor and 1/11 flowing down the 100 ohm resistor. So the current splits up according to the loop impedance, just like parallel resistors. So what we're really trying to say, what I'm really trying to say, is the electricity doesn't all stay in the wire or the PCB trace. The current flow splits amongst all the possible loop paths, whether conducted along metal, induced or radiated through insulators, PVC, FR4, air, and so on. And the proportion of the current flowing in each loop is inversely proportional to the loop impedance. Like I said a minute ago, the DC current splits between parallel capacitors. Remember, electromagnetic energy propagation, in other words, all signals, data, and power, and of course noise, only cares about loop impedances. doesn't care whether it's air or metal or whatever. All it cares about is the impedance.
Keith, I'd like to
And
again.
here's
Sorry.
Maxwell's equation.
To ask another question to our attendees.
Okay. Yeah.
Attendees, how do wanted AC currents, like signal, data, and power, flow? To the ground, in conductor loops, in any loops, in conductors or insulators? We'll give you a few seconds to answer this question. Okay, we have some votes coming in. About half of you have voted so far. We'll give you a few more seconds. Okay. And most of you voted C, 71%. Thank you.
Good for you. Great. So, as I said, here we have our first Maxwell equation. It's the only one we're going to use, actually. It's Faraday's law of electromagnetic induction. And what it tells us in engineering terms is that all currents, whether they're power, signals, or noise, whether they're differential mode or common mode, which we'll talk about in a minute, prefer to flow in the loops with the best EMC. Actually, that's not quite how Faraday would have put it. He would have said they flow in the loops that have the smallest areas and hence the least impedance. So he says they flow in the loops with the least impedance, the lowest impedance. But the loops of the smallest areas are the loops of the lowest impedances in general, and they have the smallest field patterns and therefore the best internal and external EMC. So this is the thing that caused me to write this little webinar, basically. It's the realization that all the currents want to flow in the paths that give us the best, in the smallest loops, which are the paths which give us the best EMC. We have to beware if a loop, even if it's small, has a high impedance resonance, maybe due to its dimensions or something, it might not be the preferred path at that frequency, but that's something for another day, really. All we have to do is make low impedance loops available, and the currents will naturally take them. We often feel, you know, when we design something, we often feel, oh dear, it's got much more emissions than I wanted, and why am I always battling the laws of nature? But you're not, in fact. The emissions that you get from a product are the best emissions that that arrangement of conductors and insulators can create. It's all to do with, well, let's not go there now. Maybe that's a subject for a question. So all we have to do is work with the laws of physics instead of against them. We have to understand. I got ahead of myself there. We could say that our products are trying to help us achieve good EMC. As I said a minute ago, we often feel like we're fighting our designs of good EMC, as if the laws of physics were working against us. In fact, as I said a minute ago, for any given arrangement of circuit conductors, shielding, insulators, and so on, Maxwell's equations ensure that our design is emitting the least electromagnetic fields that it can, in other words, the lowest emissions and the best immunity. Now here's the thing. Let's make this all very practical. Here's a simulation, computer simulation, using field theory, of a bent wire 20 millimeters above a metal chassis using this return path. The reference is at the bottom if you want to chase it up on the web. And I've seen this simulation done for traces on printed circuit boards and all manner of things. I've seen it done up to 10 gigahertz. And you can do it yourself with a closed field probe, actually, in a little very simple test setup. Anyway, here's this wire, 20 millimeters above this metal plane, and it's got a bend in it. So Mr. Marco Klinger did these simulations. The simulations are to do with the color shading. Red is a high current density, and dark blue is a low current density. And they drew these dotted lines on to help us understand what was going on. So the field simulator, the field solver, doesn't draw these lines on. That was done manually afterwards. And you can see that at 10 hertz, the send current goes down the wire, and it comes back on average through this diagonal here. Now you can see that the color across here is more or less uniform. That's showing us that the current density across the whole sheet of metal is the same, or more or less the same. We can see a bit of current crowding around the point contacts, which is what we might expect. Notice that there's no current on the very corners here, because why would the current flow in the wrong direction? At 100 Hertz, it's the same thing, but here's the big surprise. At a kilohertz, the current follows the path of the wire. Why is that? It's because it's a path with the lowest loop impedance. At these low frequencies, the impedance is dominated by resistance, but as the frequency increases, the inductive component has more, gets bigger, and at this particular setup, at 1 kilohertz, it's actually a smaller loop, the laws of nature, Faraday's law of induction, ensures that the return current travels back in the metal plate underneath the wire and going round the corner. At 10 kilohertz, all that happens is the current sucks itself in a bit tighter, and 100 kilohertz. So we're down to the resolution here of the cells, of the calculation cells used in the simulator. I've seen this done up to 10 gigahertz, so they're saying all that happens is the line gets dotted because of the wavelength. Dashed, I should say. Now the important thing here is that in this metal plate, even though there might be many amps of current flowing through the metal plate, because what these guys are doing was simulating a hybrid vehicle's powertrain, electric motor powertrain, even though there might be tens or hundreds of amps flowing through the metal plate, they flow through a precisely defined path in the metal plate, and in this metal plate here doesn't have any current flowing in it. Actually has a very tiny current flowing in it, but again that's something for another day. So there's a strong current underneath the wire and none anywhere else. You may find this surprising, but it's a simple test you can do yourself with a bent bit of wire, a metal plate, and a close-field probe. Another thing we need to understand is that all conductors are what we might call accidental antennas. If you look at the antenna on your wireless, on your radio or your television or something, it's just a bent piece of wire. So all wires are antennas. Being an antenna, it means the electromagnetic wave energy propagating along it, that we call electronic power signals, etc., and measures volts and amps, has a spatial field pattern, rather like what I was sketching earlier on. And the field pattern is shaped by the impedances associated with what we're calling here the send and return current loop. And that again relates to the dimensions and structures of the conductors, their associated insulators, and all of their various permeabilities and permittivities. When this energy couples, the energy radiated from, or lost, if you like, from one conductor, coupled with another conductor, we get stray currents and voltages in their impedances. And we can call this accidental antenna behavior. Of course, sometimes we actually make intentional antennas and use them for radio and wireless communications. And there's other uses of radiated electromagnetic energy too, like medical diathermy, induction heating, and so on. Accidental antennas work backwards too. If a conductor is exposed to electromagnetic or electromagnetic waves in its insulating medium, its air in other words, or whatever, then the electrical or electronic circuit that it's part of experiences the same voltage and current noise as we would need to create if we wanted to generate the exact same field pattern and field strength at the surface of the conductor. So it's sometimes called the principle of reciprocity. An antenna that works has a certain transmitting field pattern or emitting field pattern has the same kind of field pattern as the receiving antenna. So a conductor that causes electromagnetic emissions will suffer noise pickup from local fields in exactly the same way. What this means is, effectively, if we design our conductors for low emissions, it improves their immunity. The shape of the current loop defines the field patterns. The larger the area, the larger the impedance, if we ignore resonances, the larger the electromagnetic and electric and magnetic field patterns. So the straight coupling of other circuits is larger, which means a high percentage of the wanted power or signal is converted into common mode noise in a different loop. Actually, it could be differential mode noise. Anyway, it increases the distortions and noises in wanted waveforms and worsens emissions and immunity. So it's important to minimize the send and return current loop areas for all circuits to maximize signal integrity, power integrity, and EMC. Here's a little sketch, an example of differential mode electric field coupling. Here's a cross-section of our victim circuit. It's just two conductors. It's very simple. It's colored green. That doesn't mean it's ground or anything. It just happens to be the color I chose. Here's source B with its send and return conductors, and they're placed close together. There's the field around them, the electric field around them. Here's source A with its send and return conductors placed far apart, and there's the field around them. Now, these fields are drawn to scale, and you can see that even though source A is further away from the victim circuit than source B, it's in a region of stronger field from source A than it is from source B. So that's what I said on the previous slide, that making loop areas smaller makes the field patterns smaller, makes the coupling with other circuits smaller. So now we have lower crosstalk within a printed circuit board, and if this victim circuit was an antenna in an EMC test chamber, we've got less emissions. Here's an example with magnetic field coupling. Again, source B has the two wires closer together, has a more compact field pattern, couples less noise with the victim circuit than the exact same situation, except that the wires are further apart. Or they could be PCB traces, of course. We mentioned common mode and differential mode. These are different modes of wave propagation. Differential mode, sometimes called transverse or metallic, is caused by the wanted power signals which flow in the loops that we create. Common mode is also called longitudinal or antenna mode. It's caused by stray, leaked, unwanted electromagnetic energy, noise in other words, when a differential mode loops electromagnetic fields coupled with another conductor. So some of the electromagnetic energy travels as common mode current, and all currents flow in loops. Common mode currents are almost always the main cause of emissions and immunity problems because of their worst accidental antenna effects over the region, over the frequency range 1 meg to a gig. The reason is because their loops are so large. Here's a simple example. We've got an electronic circuit driving a load, we've got our red and blue conductors, we've got some kind of chassis or ground structure which the circuit is connected to. The load has a stray capacitance, and so do the wires, but I've not shown it. Here's our wanted signal traveling along the wires, and because of the imbalance in the stray capacitances between the wires and the load and everything, we get some common mode current. And the common mode current flows down both the conductors and back through the chassis or ground or metalwork or something. Now in practice, of course, the red and blue wires are close together, and this is some distance away. So the common mode loop is generally much larger than the differential mode loop. That's why, even though it's typically between 1,000 and 1/10,000th as strong as the differential mode current, it causes most of the interference. Note that radio frequency currents travel very easily through stray capacitance, flow through the air. Like I said, all the electricity does not stay in the wire. And, sorry, here's an example of common mode magnetic field coupling. Here's our send and return conductors, but because they're both carrying common mode current in the same direction, I show them as red. Here's our return path through the local metalwork, say, and here's a victim circuit. So our common mode noise can couple with victim circuits and cause interference too. You know, this victim circuit might be the antenna in an EMC test chamber. We need to talk about resonances. When a conductor resonates, it makes a perfect accidental antenna at a particular frequency. There's two causes of resonance in conductive structures. When the inductive and capacitive impedances happen to be equal, so the energy sloshes backwards and forwards from inductive to capacitive at a certain frequency, or when the geometry of the conductor interacts with the wavelength of the signals to create standing waves. We don't have a lot of time to go into all that sort of stuff, but you'll find it in all the textbooks. At the resonant frequencies, the loop impedances go wild. It could be as low as the stray series resistance, which is milliohms, or as high as the stray shunt resistance, which could be megohms, all for the same piece of wire. Anyway, with these very wild loop impedances, we get amplified accidental antenna effects. Low impedance increases magnetic field emissions, high impedance loops increases the electric field emissions. And we can get up to 100 times gain amplification of the magnetic or electric field patterns, sometimes even more. It's a resonant effect. A lot of our work in EMC is trying to prevent resonances from causing problems at the frequencies we happen to be using. Here's the thing. People often talk about earthing or grounding things as if they are some kind of perfect sink for current or voltage, usually for noise, you know. But this can't exist. Never has existed and never will exist and can't exist. All conductors have impedance, even if you call them earth or ground, so they behave as accidental, and they behave as accidental antennas. So they can't be perfect sinks. In any case, all currents flow in closed loops. So I mean all currents flow in closed loops, even noise currents flow in closed loops. So you might connect them to an earth electrode, and they'll just flow in a loop. Even if a zero impedance electromagnetic energy sink could exist, which it can't, it wouldn't play any part in signal integrity or EMC, because it's not part of the loop. Here's a very heavy-duty earthing or grounding structure in a large factory, a large facility, but it's not actually any kind of sink for the currents that are flowing around there. It is part of what we call the installation's common bonding network, local paths for stray, common mode and fault currents to flow in. Fault currents, of course, for safety. Here's a chassis with some big pieces of braid bonding everything together. This isn't an earth or a ground either, not in the sense that the earth or a ground is an infinite sink, but it is part of the cabinet's common bonding network. Again, a local path for stray, common mode and fault currents to flow. Here's a stack of printed circuit boards, or two printed circuit boards and a heatsink. Here's a braided shielded cable coming in with a shield clamp going to the chassis down here. You can see the heatsink and the 0-watt plane and the PCBs are bonded together. That goes into the chassis too. These are not earths or grounds either, but they're part of the products, what we might call the chassis, local paths for stray common mode currents to flow. And of course we want to keep these paths very, very small. Bruce Archambault of IBM did this wonderfully amusing slide many years ago, because this misconception about earthing and grounding has been common for a long time. You see, he's got all these different kinds of ground, and you know, none of them mean a thing. In fact,
Hi, Keith. I'd like to interrupt you again to ask our attendees another poll question. Okay. Is the safety ground a good sink for unwanted currents? No or yes? We'll give you a few seconds to answer. We're getting a lot of responses, and we'll give you just a few more seconds. Okay. And the majority of you voted A for no. Thank you for responding, and back to you, Keith.
Thank you. So let's move on to our example. Let's imagine we have a plastic box. In there is 3 different printed circuit boards doing different functions. This obviously is the power supply board. This is an input board, this is an output board, and they're connected together in the usual way by short bits of ribbon cable or jumper strips or whatever. You'll notice, let's wire this thing up first of all. There's some wires being plugged in. And you'll notice that there are some splits in the 0-volt plane. You know, this is maybe analog, this is digital, this is digital, this is analog. The different power supply voltages split by safety reasons, of course. And this is a terrible design. I do lots of design consultancy, and I'm often having to fix problems, and I'm often faced with products which are designed exactly like this. People think that they can control the flow of radio frequency currents by splitting the grounds. And of course they can't, because the radio frequency current will just travel through the air if it sees a lower impedance path that way. So the assumptions made in its design were that single point earthing or grounding using 0-volt plane splits between the PCBs and on the individual PCBs. As I said, that's assumed to keep the device's circulating return currents confined to certain circuit areas, preventing crosstalk of noise between them. Now this has been known to be bad practice whenever microprocessors and switch mode converters are used since 1980 or earlier, and yet people still do it. I still find people doing it. The assumption was also made that the lowest BOM cost will give the most profitable product, bill of materials cost. This has been known to be incorrect since 2000, the year 2000, when time to market became the most important issue for a product's profitability, not the cost of the components. I see lots of designs like this every year. They have poor functional performance first, especially poor signal-to-noise ratios. Their software is a bit unreliable. We do many design iterations to solve, or they do many design iterations to solve the problems, which delays the project, increases the cost, and reduces the profitability. And then, when they've got the functionality working, they do EMC testing, which they fail, and do more design iterations to solve, causing even more delays and more project costs, adding filters and shielding with increased BOM costs and reduced profitability even more. And they tend to have higher than necessary levels of warranty returns, which erodes the profitability of the product line even more. We can take a near-field probe, or sometimes called a close-field probe, and wave it around, connect it to a spectrum analyzer and wave it around. If we power this circuit up and wave the probe around, and if we draw the areas of high field strength picked up by the probe, we tend to see as red, we tend to see something like this. We find that there's noise all over the place, all down the cables and near them too, all over the PCBs and near to them, strongest in these sorts of areas, but generally all over. What this tells us is that we have a lot of common mode noise leaking out, if you like, of the circuits. So what can we do? Well, we have to realize that when we hold our probe near the PCB, what we're measuring is the wanted differential mode signals. And we also see differential mode and common mode crosstalk and noise that causes reduced signal-to-noise ratios in analog circuits and reduced digital noise margins in digital circuits, which means unreliable software. In EMC testing, it means high levels of far-field emissions, which is what they measure in an EMC test lab, and poor immunity. In real life, it means a lower proportion of satisfied customers, an increased cost of sales, because you have to spend more money on advertising and what have you to ship the product, and higher levels of warranty costs as products fail in the field because of EMI and are sent back under warranty. What can we do? Well, we know now that all currents, including stray common mode noise currents, flow in closed loops. And the loop shape and area govern the field patterns and that the current, any kind of current, prefers to flow in loops with the lower impedance. Hence, as I said before, the smallest field patterns, the best internal and external EMC. So this means that we can make a number of improvements to the circuit design and board layout and to provide all the differential and common mode currents with smaller loops, which they will naturally take. And that'll improve our EMC. It'll also improve the signal to noise and all that stuff too. Improvement number 1 is to create a radio frequency reference. We replace the multiple PCBs with a single board as a common conductor, which is almost always the 0 volts plane, over the entire area. We call this the radio frequency reference. It's a solid, continuous copper PCB plane that lies underneath and extends beyond all the devices and the traces. So, because it's a solid metal plane, it has a very low impedance. The impedance we need depends on the devices and the EMC specs, but it's almost always much less than an ohm. And a solid metal plane close to the traces and the devices does that for us. We have to achieve this low impedance over the frequency range that we want to control to avoid causing and suffering EMI. And that frequency range is basically all the differential mode frequencies created by the devices and all of the frequencies that are present in the environment that the thing is going to be used in. That's emissions and immunity. Improvement number 2 is DC supply decoupling. We design the decoupling between the DC power rails and now our radio frequency reference to achieve a low impedance. How low depends on the devices and the specs, but it's always going to be less than an ohm over the frequency range that we need to control to prevent the product causing the suffering EMI. Now, the AC, the fluctuating differential mode currents in the DC rails, can now flow in tiny loops very close to the devices that caused them. They don't have to flow in large areas, they just flow in the decoupling capacitors, the local decoupling capacitors. So they do, because they prefer to flow in small loops. And they don't flow widely around the radio frequency reference or the power distribution network. So the first thing we're doing here is making small areas of differential mode near fields that create much less common mode noise. Next thing then is to filter all the cables. We need to add direct bonds for cables connected to 0 volts, conductors connected to 0 volts, or we add filters to the radio frequency reference on all the traces which connect to off-board conductors. Doesn't matter what they're used for. If they could be mechanical, things like brackets or hydraulic pipes or pneumatic pipes. If they're metal and they exit the printed circuit board, they have to be bonded to the radio frequency reference, either directly or with a filter. The filter should at least be a capacitor to the reference. Generally speaking, we make more complex filters by having capacitors and then resistors or soft ferrites, but that's too much to go into in this short webinar. Anyway, we put these capacitors or filters where the traces connect to the conductors at the point where they enter or exit the printed circuit board. This provides a low impedance path for the common mode currents on the wires, which would otherwise leak out from the board into the conductors. And the conductors, of course, long conductors, make wonderful accidental antennas. We're always trying to achieve less than an ohm, these low impedance paths. Sometimes it's not so easy. We could, of course, have shielded all the cables. I've not mentioned that in the slides. But if you've got a plastic box, you generally are not wanting to shield your cables anyway. And shielded cables are expensive. So we're trying to keep the cost down. Here's our improved example. Here's our plastic enclosure, single printed circuit board, with one overall radio frequency reference plane, and there's obviously a plane split here for safety reasons in the power supply area, but no other plane splits. There's a bunch of filters on all the inputs, and a bunch of filters on all the outputs, and a bunch of filters on the mains. Let's measure that now with our close field probe. This is what we get. Typically, we'll see the same field intensity that we saw before close to these processing devices and close to these switch mode devices. But away from them, the field that we measure with our probe will drop off very rapidly. So we don't see a great big sort of cloud of near field noise all around the whole board. We're bound to see these hot spots on the chips because what we're picking up is their differential mode fields, the actual fields which are the currents due to their operation. But we aren't seeing any common mode noise. So this has very good EMC. And all we've done is a few simple things. As I said earlier, these good EMC design techniques work exactly as well for immunity as they do for emissions, because they employ the fundamentals of electromagnetism to make the field patterns and wave propagation as compact as possible, dramatically reducing the electromagnetic coupling in the printed circuit boards and between components and traces, reducing emissions and improving immunity. So we improve our internal EMC, our power integrity and signal integrity, so we don't have to have so many design iterations to get the product working to spec and get the software reliable and stable. It improves external EMC, and it also improves reliability. This is the thing people often overlook. Products designed to have better EMC work more reliably in real life and reduce the warranty costs. So to wrap up this very brief webinar, all electrical and electronic activities, currents if you like, are really electromagnetic energy traveling as waves. Connecting them to the safety earth or ground has no effect at all, so it's unimportant and unnecessary. It may be necessary for safety, but it doesn't have much effect on the EMC. In fact, I've often removed ground connections where safety allowed me to do and improve the EMC. We can easily design circuits and printed circuit boards to provide lots of small, low impedance current loops for the wanted differential mode and the stray common mode currents. The electromagnetic waves naturally prefer to flow in those routes. So by working with the laws of physics, we automatically achieve very compact field patterns, which are the best for internal and external EMC and best for financial success. And that's the end.
Thank you so much, Keith. That was a great.
I hope you enjoyed that.
Thank you. We would like to have a call for final questions. Please enter any last questions you may have in the navigation pane. We're running a little close on time, but we're going to try to get to as many as we can. And if you need additional information on this topic, there's a vast amount of content on our website, interferencetechnology.com. You can also email us at info@interferencetechnology.com with specific needs, and we can direct you accordingly. Keith, here's a question for you. Why do currents flow in loops?
Oh, right. Well, it comes down to the law of conservation of energy. If you take let's just take a point along the wire or a printed circuit board trace. If you imagine there's a current leaving it, say, to the right, so many milliamps or something, then so many milliamps has to join it from the left. Otherwise, you get an energy imbalance at that point. You're creating energy out of nothing, which we know we can't do. Otherwise, electricity would be free, and it certainly isn't. So if you follow that round, you find that the currents, if you take that description around the whole circuit, you find that currents always have to flow in loops. Otherwise, somewhere in the circuit, we'd be creating energy out of thin air. That's it.
Okay. Keith, how does a current know where to flow when it has multiple possible loops but hasn't yet traveled far enough along them to experience their impedances?
Whoa. Oh, I love this question. It's a very, well, I thought it was a very tricky question when it occurred to me about 10 years ago. I knew that currents flowed in loops, but in order for the energy balance thing to work properly, the send and return currents have to be simultaneous. And I couldn't figure out how, if you had say, some printed circuit board 0-volt plane or some kind of chassis, and you had currents flying back through the plane or the chassis or whatever, having multiple paths, I couldn't figure out, because I was a circuit designer, how they knew which path to flow back in. How did you know in advance what would be the loop with the lowest impedance? Because you couldn't see ahead of you, if you see what you mean. You see what I mean? Like, you're driving down the road and it's dark, you can only see so far. Anyway, as it happened, I bumped into my old electromagnetics tutor from university at a conference. And I said, you know, this is really puzzling me. And he recommended a book by, dear me, I've forgotten his name. That's stupid. Anyway, he's the guy who invented quantum mechanics. I'll think of his name in a minute. Very famous American chap. And how stupid of me to forget his name. Anyway, it turns out it's all to do with quantum mechanics. This guy discovered that you could figure out how quantum mechanics worked by integrating the movement of particles, if you like, over the entirety of space and time, including negative time. When you asked him how, you know, that worked, he said, "Don't ask. We don't know, but we do know that this theory works." So what we can think of is it's as if the return current, the current in our circuit, explores all the possible paths through the entire universe, and all of the paths cancel out except for the one which has the least field energy. Oh.
Thank you,
I keep
Keith.
thinking of the wrong guy's name. I knew I should have got it.
Why do good design practices for emissions also work just as well for improving immunity?
Yes, that used to amaze customers with that. We'd do some emissions testing in a laboratory and say, oh, look, you've got strong emissions at a certain frequency. That means you're going to have an immunity problem at that frequency. And if you have emissions at a certain frequency, it says, A, that your circuit is making making electrical activity at that frequency, and B, there's some kind of accidental antenna that's radiating it away from the printed circuit board as common mode noise. Well, accidental antennas work both ways, so when you're doing the immunity test, that antenna will pick up preferentially at that frequency because it happens to resonate at it or something. And of course that frequency is one of the operational frequencies of the circuit, so it's quite likely to interfere with it. So in this way we can see that the things that cause emissions are also the design features, if you like, that cause emissions, are also the design features that cause poor immunity. That's that.
Thank you, Keith. We got a few responses. Are either of the names that you were trying to recall Richard Feynman or Max Planck of the author?
It's Richard Feynman. Yes, it's Dick Feynman, of course. Thank you very much.
Yep. One of our attendees actually answered the question.
Oh, good for you.
We've received so many great questions that we will try to address in the future. Keith, thank you again for your time and expertise. Webinar attendees, if you have any more questions that we didn't answer here, please send us an email at info@interferencetechnology.com. A recording of this email will be available on our website, interferencetechnology.com. We will also send a link to all participants shortly. Thank you for attending.